contrast curves. So to give you all a brief reminder, just for those who aren't familiar with the concept of contrast curves, we want to turn this image, we have an image here where we know, okay, great, we found a companion. But what we would really like to know is, as a function of separation in this image, how bright would a companion need to be for us to be able to detect it? So this is this example here where you create this curve and you can say, well, anything under this line, anything that faint or that separation, we wouldn't be able to detect. And anything above the line, we would be able to detect. And that's kind of the metric we want to produce from these images. And we can do that pretty easily using spaceKLIP and PyClip. But the first thing we need to do is tell it, what's the contrast relative to? We need to know, from this image, how bright something is relative to the star we're observing. That's the kind of metric we're interested in, the contrast. So to do that, spaceKLIP requires, at the moment, an input stellar model. So here's an example for what I used in the HIP 65426b observations. You can see we fit the available photometry for this star, HIP 65426, and we've produced this best fit model that has some slight increase due to a disk component that we think might be there to kind of input to spaceKLIP. And what spaceKLIP will do is it will use this model and use the bandpass of the JWST filters to be able to predict how bright the star is in those filters. Now, some people, you might be thinking, well, that seems like a convoluted way to do it. Why can't you just use the image of the star in the images you've got already? And there's a couple of issues with that. Firstly, apart from, the first filter you perform the target acquisition in for NearCam, all the other filters you observe in, you won't have a actual unblocked, non-coronagraphic image of the star. So you can't measure its flux directly. The only way you could do it is maybe by using a web PSF model again and trying to model the PSF of the star and fitting the flux that way. We haven't really explored that yet. Maybe that has some potential, but it's just a more complicated process. So if you don't have a stellar model or you can't be bothered to do all this like complicated fitting, you can also just grab a Vizia Vo table with the input spectral type, and that's also compatible. And I did put a link here so you can see what this looks like. If you go to this website, Vizia CDS, you can see it's the photometry viewer on Vizia. And you also tell the code a spectral type, and you give it this Vizia data of just, this as a function of wavelength, what the measured flux of this object is. Then spaceKLIP will go away and, guess a model for the spectral type you gave it and fit this flux for you. But I do think for like a more formal analysis, you should probably be looking at making your own stellar model. Okay. So we do need to mask companions. So I touched on this a minute ago for the image registration. Maybe you don't, but for the contrast estimation, you definitely do. Because if you have a giant blob of light in your image, then when you do that contrast analysis, it's going to think that's just noise. It can't treat it any differently. So what we do is we can kind of mask this out. At the moment, PyClip and spaceKLIP, just has these circular or PA-based masks. So we can put this circular blob where we know the planet is, or if you wanted, you could define like a slice in PA where you'd want to block that out too. Definitely more complex approaches may be necessary if you really want to dig into things. I think if you just want to first look, this is fine, or an estimate of the contrast. But because the PSF shape is so complex, it's a bit tricky to put together like the perfect mask. Okay, so one thing I want to touch on briefly is raw versus calibrated contrast. So I mentioned earlier, you can tweak the number of PCA modes, the number of like principal components to subtract away that stellar PSF. And what happens is as you scale the number of those modes, you start to introduce over subtraction. The higher number of modes, it starts to think light that it's from the planet, maybe isn't from the planet, it's from the star instead. And that can heavily impact the flux. You can see here as we move to higher modes, boom, the flux drops and we can't see the planet as clearly anymore. And you really don't want that affecting your estimates of contrast. You don't want to be underestimating or overestimating the performance. So what spaceKLIP and particularly with PyClip can do is it can model that that change to kind of understand, how much is the CLIP subtraction process itself chewing away at the flux of potential companions in the image. So we do that. The way we do this is in spaceKLIP, we inject using a WebPSF model of an object and recover the flux of a bunch of planets at different separations. Here I haven't masked the companion itself, just so you could see, but you might want to mask that if you really want to measure the contrast. But also, if you're doing this at a whole bunch of PAs and separations, then any sort of impact of that companion, particularly if you're avoiding the bad PAs, is going to be sort of washed out when you do a median as a function of separation. And you can see here, like, we're trying to inject as many as possible in each image without sort of overlapping too much. Okay, so after you've injected all these planets and recovered how much flux you received, you can look at that as a function of separation to get this kind of gauge of the throughput. How much light is actually being received after you've performed the PSF subtraction. And what you'll see is actually, for this particular case, you have this huge drop off close to the star. And this is actually just the throughput of the coronagraph itself, especially this extra bump here is 2. This is just the profile of the coronagraph. So the coronagraph itself won't just diminish the flux from the star, it will also diminish the flux from the planet. And this process will capture that. But towards these wider separations where the coronagraph really shouldn't have too much influence, you can see the throughput still isn't quite 1. And that's kind of this PSF subtraction kind of chewing into the companion flux itself. So what we do is we take that throughput and we can divide our contrast curve by it to kind of get this calibrated contrast of what the true contrast is as a function of separation. You can see this really heavily influences these shorter separations as opposed to the wider ones where it's a relatively small effect. I will say that for these images that I've been playing around with, we haven't seen the CLIP throughput be really significant. Like here you're seeing it's sort of like maybe 5%, 7%. But who knows, maybe in other observations it would be more significant, although I don't think that would be the case. Okay, so we'll move to the live demo again. Okay, so this raw contrast step, what are we going to set up? Well, we're going to tell it what of the subtraction we performed earlier. We performed that subtraction, a bunch of different basis vectors. This is just defining which KL mode we want to use for future steps, as well as this PSF spec, PSF star. This is the spectrum for a companion and the spectrum for the star. These actually won't be used right now. I think I accidentally put these in this step, but I'm just touching on them because they're there. But the things we really care about are these things below. So contrast use file. So this is just, you can tell it if you want to use a specific different file. This is more for the background subtraction to measure the contrast. You can tell it, do you want to repeat that image registration process when you're performing the contrast, or do you just want to use the values you already have? That contrast curve is a function of separation. We can provide in a different range of resolutions. You could do it on the per pixel level, or you could do it in terms of something more physical like lambda by d. So here we've ticked default, which is just we'll give the contrast to every lambda by d as a function of separation. This is for how we do the calibration of the contrast curve. What method do you want to use to fit those points that I just showed you? So this is just a median. And then here again, we're just defining, where the planet is for the masking, and then how large of a circle we want to mask at that location. Now, what I am going to show you today is just the raw contrast, because certainly the calibrated contrast takes a much longer time. That process of injection and recovery, where you have to perform this PSF subtraction on every new injected image, can take a bit of time. We're talking sort of 10 to 30 minutes for the images I'm using here, and it could be longer if you have more integrations. But I will show you the raw contrast because that's very, very quick to run. So if we run that, and again, we're just calling pipeline.rawContrast, you can see it's produced this new file. It's produced this image telling us, oh, here is the scene. Here's the companion you marked to mask, and here's what it looks like after you mask it. And then it's quickly produced us this contrast curve. So you can see here, like at these close separations, it's kind of closely matching what we expected. But these wide separations, maybe we're getting a few crazy bumps. And that's directly because of this issue here. At these wider separations, you can see there's a ton of companions that I haven't bothered to mask. And that's reflected in the contrast. The contrast thinks that you're less likely to detect things at those separations, which isn't true. So really, in your image, you want to be careful to mask anything that you don't think is, like just the background of your image. And then also there's just a quick plot here for the contrast as a function of separation, just on a shorter scale. What we did just change actually recently is now the raw contrast will include the effect of the coronagraphic throughput. Not the clip throughput, that's really the process that takes a lot of time. But this is a bit more representative because we can cover that closer separation region much better. And then you'll also see we have this JSON file. This is just the contrast curve itself. So if you want to go away and plot this in a fancier way or look at it in more detail, you can see here. So we've got the separations in arc seconds. We've got the contrast for the different KL modes all the way through, as well as some like values for how bright the star is in Vegamag in this filter.